Welcome back to Dr. Liu's VCE Chemistry channel. Today, we'll break down the electrolysis and rechargeable cells questions from the 2024 NHT Chemistry exam. My explanations might need refinement, so I welcome corrections or feedback from teachers, parents, or students. Faraday's first law of electrolysis establishes a direct proportionality between the amount of substance produced at each electrode and the quantity of charge flowing through the cell. To verify this law, the charge quantity must be accurately measured. Since charge is the product of current and time, one could vary the current while keeping time constant, or vice versa. Factors like electrode volume, voltage across the electrodes, and temperature are not relevant to Faraday's first law. Compare electrolytic and galvanic cells. In both galvanic and electrolytic cells, oxidation consistently occurs at the anode, resulting in the release of electrons that then travel to the cathode. Notably, the anode in an electrolytic cell carries a positive charge. Unlike galvanic cells, electrolytic cells do not require the physical separation of reactants. Furthermore, the overall chemical reaction within an electrolytic cell is typically an endothermic process, meaning the products possess higher stored chemical energy than the reactants. As secondary cells, lithium-ion batteries are widely utilized in devices like mobile phones. The magnitude of current flowing through such a cell is a direct consequence of the rate at which chemical reactions occur. This implies that modifying the surface area of an electrode can influence the frequency of effective reactant collisions, thereby affecting the resulting current. However, the spatial arrangement of the reductant and oxidant does not dictate either the speed at which a reaction proceeds or its ultimate yield. Nickel-hydrogen cells are rechargeable. The oxidizing agent in a reaction can be identified by analyzing changes in oxidation numbers. During discharge, electrons flow from nickel's lower oxidation state in NiOH, Ni, +2, to its higher oxidation state in NiOOH, Ni, +3. Therefore, NiOOH acts as the oxidizing agent when a nickel-hydrogen cell discharges. Nickel-hydrogen cells are rechargeable. The negative electrode material for these cells must possess specific properties. It should be porous to facilitate reactions, non-reactive to ensure stability, and conductive to allow electron flow. While materials like graphite, platinum, and gold exhibit some of these characteristics, the negative electrode in nickel-hydrogen cells primarily utilizes hydrogen-absorbing alloys specifically engineered to meet these requirements. In a nickel-hydrogen cell, discharge involves NiOOH acting as the electron acceptor and hydrogen losing electrons. Conversely, recharging is the reverse electrochemical reaction, where NiOH becomes the electron donor, and water undergoes reduction by gaining electrons. Under standard conditions, the potential difference between the anode and cathode is calculated as 1.35 V, 0.52 V minus 0.83 V. Therefore, the voltage required to recharge the nickel-hydrogen cell under these same conditions must be greater than 1.35 V. This greater than criterion is crucial for the mark. As a nickel-hydrogen cell approaches the end of its lifespan, it experiences a reduced capacity to be fully recharged. Consequently, the battery's operational duration between recharges significantly shortens. Simply attributing this to lower efficiency does not fully explain these specific performance degradations. As nickel-hydrogen cells recharge, their hydroxide ions lose electrons, generating oxygen gas. This is how oxygen can be produced during the recharging process. The oxygen generated during recharging possesses an E value that closely matches that of the anticipated NiOH. This means that any oxygen produced can effectively react with hydrogen during the discharge cycle, forming water. As a result, the nickel-hydrogen cell's operation will remain largely unaffected, and its output will be very similar, demonstrating that oxygen production is not detrimental. The electrolysis of concentrated lithium chloride solutions produces lithium hydroxide. During this process, electrons are gained at the cathode, which should be connected to the negative terminal of the power supply. Acting as a selective barrier, the membrane permits the passage of small positive ions, such as Li, but prevents larger anions, like Cl or O, from crossing. This functionality is crucial for separating and isolating the LiOH product. Chlorine gas is known to be produced at the anode by the oxidation of chloride ions. Correspondingly, hydrogen gas is expected to be produced at the cathode through the reduction of water. Replacing the graphite anode with zinc would result in zinc oxidation, as zinc metal is a stronger reductant than chloride ions. Consequently, the lithium hydroxide product could be contaminated by zinc ions. To produce 0.5 g of chlorine gas, using this electrolysis cell at 0.895 A, the required time can be determined using Faraday's law. This involves first converting the mass of chlorine gas into moles, then calculating the moles of electrons required by the ratio of chlorine gas to electrons. Next, the coulombs of electrons are determined using Faraday's constant, and finally, the time required is calculated. This section is a significant component, accounting for 23 marks, 19.2% of 120 total points, distributed across 3 multiple choice and 2 short answer questions. Faraday's first law: the amount of substance produced at electrodes is directly proportional to charge flow, tested by measuring current with constant time. Electrolytic versus galvanic cells both have oxidation at the anode and electron flow from the anode to the cathode. Key differences: electrolytic cell anodes are positive, and the overall reaction is typically endothermic. Lithium-ion cells, performance is influenced by electrode surface area. Nickel-hydrogen cells, the negative electrode material should be porous, non-reactive, and conductive. Reduced capacity to be fully recharged signifies the end of cell life. Oxygen is produced during recharging and consumed to form water during discharge. Industrial electrolysis of brine, membrane function, permits small cations, but blocks larger anions. Gases produced and production time: chlorine gas is produced at the anode, and hydrogen gas at the cathode. Specifically, producing 0.500 g of Cl2 with 0.895 A current takes 1,518 seconds. Anode replacement impact: replacing the graphite anode with zinc would lead to zinc oxidation, potentially contaminating the lithium hydroxide product. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.